Good morning, students. We have a decent population now. Let us start. Let us start our class. Well, in today's topic, there won't be any surprises kind of thing or new thing. Like, we'll just.
Excuse me, sir. Sir, can you please start the
Yes.
recording?
Yeah. I forgot to do that. So, in today's class, will be it will be like a recap of whatever you have studied in your 12th or graduation level. It's like we'll be talking about determinants. And we'll lay the foundation for the next class. Okay, so by the way, what is the complexity of determinant?
Sir, it
Okay,
depends
because
how you have represented it.
it depends how you represented it. Okay, that's correct. But then how I represent it, that is important, right? That's fine. So, so determinants are usually we find determinants for square matrices, and so determinants of a matrix of one element, sorry, it should not be square. Determinants of one element. This is how we represent it. And determinants of 2 cross 2, this is how we write it. AD minus BC. That's how I write it actually. Uh, we'll quickly go through some of the properties of determinant. One of the property is property 1. Determinant, let me write DET, or in small, let me write, that is better. Determinant of identity matrix, how much?
One.
1. So that is what an example is. Okay. P2, when rows are exchanged, or interchanged, not exchanged, interchanged in fact. Interchange would be the perfect word. INTERCH. When rows are interchanged, the determinant changes its sign. That is, if I have a matrix like this, and I have another matrix like this, where the rows are swapped, interchange. So the equality or inequality sign that I will give here would be minus. The next property, uh, a determinant of a matrix is a linear function of the first row. By the term linearity, by the term linear, this subject is linear algebra, so I hope you know what linear is. We have something like a multiplicand, scalar quantity or addition. That way we actually represent. So if we have a matrix like A, B, C, D, and I multiply this one with let us say lambda. I have multiplied the row, one of the row with a lambda. So one of the row is multiplied with a scalar quantity. So this actually lambda times A, B, C, D, which is actually not true, which is actually not true in case of matrices. If a matrix is to be multiplied with a scalar quantity, let us say k is equal to k times a, b, c, d, then it becomes actually k a, k b, k c, k d, isn't it? But this is the case in the case. This is the case when it is a matrix. But in the case of determinants, this is row specific actually. This you can very well prove it. This is one of the property of linearity. Another property is the if I have a matrix like again A, C, D, and sorry B, and this row is, let us say, I. This particular row, it is a summation of two elements again. I can represent it as okay. So these are the three important properties of a determinant. Now, from these three properties, let us derive some more properties, some auxiliary properties, like they are also important, very important. So property number one, well, I say a determinant, the property 3 says the determinant of a matrix is a linear function of the first row. So linear function of the first row. But then here it says when rows are interchanged, the determinant changes its sign. So basically I can interchange the rows, and the same thing can be applied on the second row also. The same thing is applied on the second row as well. If CD is interchanged for this particular, for this the right hand side matrix, the same thing applied. So basically this we can extend and say that determinant is a linear function of all rows. And later on we will find that it's not just rows, it's also columns. Okay. So another property, if two rows are equal, determinant is equal to 0. If two rows are the same, the determinant is 0. If elements of one of the rows are all zeros, determinant is equal to 0. Matrix is not invertible if determinant is equal to 0. Well, this is again important. Like A matrix times B matrix and its determinant is equal to however A plus B is not equal to, this is not true. Similarly, we can write that determinant of A inverse is equal to 1 by similarly we can write A transpose this itself proves that this is it's a function of rows as well as columns and all those things. Number 8, determinant of diagonal matrix. Let me write it as D. So what is that? Determinant of diagonal matrix. That is product of diagonal elements. Similarly, determinant of lower triangular matrix, that's also product of diagonal element. Determinants of upper triangular matrix, that is also product of diagonal elements. Okay. One more important property, that is usually we do it using that Gaussian elimination. What is that? I mean, row, whenever a row is scaled and added with another row, the determinant of matrix doesn't change. Okay. So lot many properties are there, but then the bottom line is being a student of computer science, I only look for how fast I can compute everything. So a 2 cross 2 matrix, I say it is A, B, C, D. So A, D minus B, C. So if it is a 3 cross 3, A, B, C, D, E, F, G, H, I. So this is actually what we do. We freeze one of the rows and the corresponding column, isn't it? This is what we do. We freeze one row and we freeze one row and one column. We freeze one row and one column, and from there we find out A times E, F, H, I minus B times D, F, G, I. That is the next time I freeze this particular row, this particular column, and the third time I freeze another column, and that is how I write it: C times D, E, G, H. And whenever I write it completely. Let me write it. AEI minus A HF or for the sake of symmetry, let me write it in this way. AFH minus BDI plus BFG plus CDH minus CEG. 1, 2, 3, 4, 5, 6. Yeah. So what I want to convey here, these are the things you know. That is what someone said, that this is the way you represent the matrix. One of you said that the way you represent the matrix, that way only the complexity increases. And this is the this is the most common way that we compute determinant of a matrix. And look at this. We have how many elements here? How many elements? 6. 6 components are there. 6 components are to be evaluated in 6. 1, 2, 3, 4, 5. 6 components are to be evaluated. And here we have 2 components are to be evaluated. And if you check, it is like A times determinant of a submatrix, B times determinant of a submatrix, C times determinant of a submatrix. So I have frozen one row and all the submatrix combinations are evaluated. And the lowest submatrix that I am taking is 2 cross 2. So when this is 4 cross 4, the same thing you start doing, but then there are 4 elements along the first row. So 4 times first row, first element will be having a 3 cross 3 matrix, determinant of 3 cross 3. That will be evaluated by another 3 number of 2 cross 2 matrices. So like that, if you compute, so that becomes 4 times 3 times 2 times, that is equal to 24 components in a 4 cross 4 matrix. Determinant of 4 cross 4 matrix, for 24 components would be there. Or basically speaking, for an n cross n matrix, this is actually factorial n. And for a computer science guy, if anything factorial, then you are in big soup. Order of factorial, it's a deadly one that I need not say. So at best, what you can go with this process is actually say factorial 12, factorial 15 or 16, something like that. That will be feasible at least to compute. It's 15 cross 15 or 16 cross 16. After that, I believe you can go. That will be, I mean, you can compute that. I mean, beyond also that you can compute, but then that will be infeasible. too much of expense, time expense. So what are the solution? Solution lies with the properties. The solution lies with all these properties, and the important properties are these three that highlights here: number 8, number 9, number 10. So just a second, I got. Okay, so what happened? Just as okay. Is there anything else that I'm missing? Um, yeah, there is one more important concept that we call it as cofactor minor. So, what is a minor? A minor is the determinant of any square submatrix. So, if I am having a matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, can I call 5, 6, 8, 9 as a minor? Can I call this as a minor?
Yes, sir, it would be minor of first component.
2, 3, can I call it as a minor?
It's not a square submatrix.
That's right. It's not a square. It's not a square, so I cannot call it as a minor. What about 4, 6, 7, 9?
Yes, sir, it's a minor of second component too.
That's right. What about 1, 2, 5, 6?
Sir, elements are not in proper order.
This is not a minor. This cannot be a submatrix. This is not square. Though it is a submatrix, it is not square. and though it is a square, it is not a submatrix. Okay, so what's a cofactor? So if a matrix is given A, let me write the matrix as A. The system many a time doesn't respond it properly. Aij. So is the matrix. So cofactor of element Aij. So cofactor of Aij is equal to minus 1 to the power I plus j times determinant of minor of Aij, right? Okay. But then this is again a very expensive way of calculating. That is what I was trying to convey at that time. That this is exactly what we did for this 3 cross 3 matrix. This is exactly what we did for the 3 cross 3 matrix. No, no, no. Uh, this cofactor definition, I missed one line, right? Cofactor of Aij equal to minus 1 to the power I plus j times determinant of minor of Aij times Aij, right? It is Aij. Okay, that's correct now. So that is what I was trying to convey here, that this is very an expensive way of calculating the things. Now, in fact, we haven't seen that LU decomposition and all those things. I haven't told you. That is quite common. You can very well read that portion. But I'll take one of the class to just quickly recap the way this determinant is being done. So that will
Excuse me,
also
sir.
be quickly recapped. Yeah.
Sir, why we are multiplying Aij in cofactor of Aij? I think,
Hello.
sir,
Yes.
so I was asking that why we are multiplying Aij in cofactor of Aij.
I was talking about the um,
Cofactor of Aij1.
yeah, that's what cofactor of the element Aij. It's actually a scalar quantity. Uh, okay, you do not multiply Aij, right?
Yes, sir.
It's only the right. Its determinant is not a series summation of the cofactors, rather cofactor times Aij. So cofactor will be only this much, right. Um, that's correct. Cofactor only will be this much. Minus 1 to the power I plus j, that is just to segregate the even and odd term. And determinant of the minor of the Aij. That's correct. Okay. So let's take an example, one more. We have a couple of minutes left. One, two, three, minus two, three, two, three, minus one, one. Can we find the determinant of this? Let me write in this way. Row 2 is equal to row 2 plus 2 times row 1. This is one of the property. This is one of the properties and it doesn't change the determinant. So what happens with this? 2 times row 1 plus row 2. So this particular element becomes 0. So let me write 1, 1, 2, 3, 3 minus 1, 1, and this becomes 0. 2 times row 1 plus 4 plus 3 is 7. 6 plus 2 is 8. Right? Next, let me make another move. That is R3 is equal to R3 plus minus 3 times R1. Mm. So 1, 2, 3, 0, 7, 8. This becomes 0. Mm, minus 6 minus 1 minus 7. Minus 9 plus 1 minus 8. Mhm. Okay, what is next? R3 is equal to R3 plus R2 1 2 3 0 7 8 0 0 0. So the number of computers reduces drastically. Here it became 0, but then not always it will be 0. Okay, so we'll try to find out how more easily we can find determinants in our subsequent class, as well as like what way it's a part of linear algebra, but then this will lay the foundation for something more typical things. And there is one more short class I will take, that is on the LU decompositions and everything. That is again that will be again like a quick recap of whatever you have seen. Mm, well, till then we'll stop here. Thank you.